It's going to be so fun to read 30 pages. Thanks for showing that not on this specific page, but on the next page. Let's see if I got any more random grades. Probably not. Man, when am I ever going to get any grades for this class? Well, thankfully we don't have to do any algebra. I mean, algebra. Calculus. Why am I thinking it's not even that hard? Yay. How many people get zeros on a test? Stop. Says the mean is 70. Meters, the measure of central tendency. Standard deviation is nothing. Oh, okay. No, me is less than 7. Normal distribution. It's very complicated. Ooh. Hey, guess what that means? They say for the sake of completeness, that means it's not going to be on the test. 1 over the square root of 2 multiplied by pi multiplied by standard deviation times e to the power of negative x minus, I don't remember what that is mean, squared divided by 2 times the standard deviation squared. That's complicated. Man. The mean can be any number. If you increase or decrease the mean, you will shift the curve to the right or left. If you, the standard deviation must be positive. When it's small, it's a more peaked curve, and when it's large, it's standard. When it's a small variation, that the curve is that. So this refers to, this notation is normal mean of -2, standard deviation of 1. Funny. Stop! Standardizing z-values. Stop! Standard normal has a mean of 0, standard deviation of 1. That's also referred to as the z-distribution. In order to standardize the variable, you subtract its mean and then divide the difference. And then you divide it by the standard deviation. Oh. The z-value is the number of standard deviations to the right or left of the mean. Thanks for showing this as a 5.3, even though this is 5.54. Oh. If the z-value for some student is 2, then this student score is 2 standard deviations above the mean. The annual returns for 30 mutual funds. Find the interpret z-value. Okay, they have a bunch of annual returns. They calculated all the z-values. Ooh. Oh. Okay, so Oh, okay, well, I mean, this is not going to be important for the quiz. I'm just trying to study so I can take a quiz. So, anyways, because I'm technically supposed to do the homework today, but the professor made an announcement which kind of implied that I didn't have to do it today. um, um, so, yeah, I didn't really read that part that much. I'm just trying to get 100% of the quiz. That's all I'm doing right now. Stop. You sniffed. Really? Stupid tables. What is the probability that... Oh, you sniffed. That a standard, normal, random variable is less than 1.35. And then you look at a table. How about no? How about no? Where's the formula? What, this? Oh, come on. Tables. Why can't you just use an equation to find it or something? Anyways. If the probability is this, the probability of being to the left of this number is 0.75. So now, we will show you how to do it in Excel. Oh, fun. Well, isn't that part not going to be on the quiz? The quiz is just conceptual stuff. And then the homework problems are how to do it on Excel. They use the function norm.dist and norm.s.dist standard, and that applies to anyone. The inverse function is norm.in and norm. So those functions return the probability that a normally distributed variable is less than 35. You do that parenthesis x comma mean comma standard deviation true. What is the true mean and date? What's true? You supply a number, and true is, you could either write true or 1. Well, guess what? 1 is easier. Why on earth would you say true? The cumulative normal probability. It's a nuisance to remember to type it? Are you kidding me? If you supply the probability, it will return the percentile. Okay. Now an example. Okay, that I don't need to read this right now. I'm just trying to study for the quiz. Oh, come on, we're still not even done with 5-4. Dang it. The empirical rules. Dude, I searched across the entire book for the empirical rules, and that's the only place I could find it. Or in that one other chapter. Did I just not look at it correctly? Come on. It must be a normally distributed function. So they just derived all of those probabilities right there, I know. Yeah, weighted sums. Yeah. If you create a weighted sum of normally distributed random variables, the weighted sum is also normally distributed. What a fun time. Is that going to be on a quiz? If x1 through xn are n independent and normally distributed random variables with the common mean and common standard deviation, the sum of all variables is normally distributed. The sum of the variables is normally distributed. With mean, sum of means, variance, sum of variances, and square root, and standard deviation. If a through 1 through an are any constants, you will need this fact to solve a few problems in the chapter. Something or other. That's one. No! Now they're going to apply it to several business problems, but guess what? I don't really need that right now. I'm just trying to study for the quiz. The conceptual quiz that will not include any math problems. I'm pretty sure. So, we can skip 5-4H for right now, but we will probably need to look at it later. Although we might not have to look at it that much, because the professor said she would provide us with a video explaining how to do problems. So I might not have to read much of it. So anyways, thank goodness I can skip all this. And then there's problems I can skip. Oh, wait. Tons of problems. And now we only have 3 more sections, and we have already gotten halfway through the reading. In only 20 minutes, we've already gotten halfway done with the readings. The binomial distribution, normal distribution, and then we have a binomial distribution when sampling from 2 types of members and perform a sequence of identical experiments, each of which has only 2 possible outcomes. Any experiment that can be repeated many times. There's a trial. The outcomes are independent. Each trial is either a success or a failure. Probability of a success in a trial as P. Probability of a failure is 1 minus P. N is the number of trials. There are N independent identical trials where the probability of success is P and the probability of failure is 1 minus P. Define X to be the random number of successes in the N trials. And N has a binomial distribution with parameters N and P. Distribution of the number of successes in 100 trials where the probability of success is 0.3 at each trial. Number of 3 trials. X represents number of heads in each 3 flips of a coin. The possible values. What? Wait, what? What? What are you talking about? Why on earth is that the case? How does that work? Really? Now you're just confusing my small brain, apparently. How are the possible values of X 0, 1, 2, or 3? How is that possible? That doesn't make sense. What? What? There are 8 possible outcomes. Oh, I get it. Never mind. It's the number of successes. X is the number of heads in 3 flips of a coin. You can either get 0, 1, 2, or 3. Whoa. We have 1, 3, 3, and 1. Therefore, so we have all those. Probability that X equals K. Binomial.dist. General form is binomial.dist. Whoopsies. True if you want the probability of less than or equal to this, and false if you want probability of exactly this successes. What a fun time, everybody. Whoa. Oh. I don't feel like reading an example. Okay. The mean and standard deviation of the binomial distribution. The mean, why do they call it E of X? It's equal to N times P. The standard deviation equals the square root of NP times 1 minus P. I don't care about the intuitive explanation, so dang it. The empirical rules, why do they only approximately apply? there's a 5% defect rate. That was funny. The mean is 50. Standard deviation is 6.89. Therefore, so it's approximately 95% certain to be within 50 plus or minus 2 times the standard deviation, or approximately from 36 to 64. So it's slightly beyond 3 standard deviations. It is highly unlikely that there will be 75 or more defective parts. The population is N members, of whom NM are men and W are women. And if you sample N of these randomly, you are typically interested in the composition of the sample. You might expect the number of men to be binomially distributed. Without replacement, you can always sample each member of the population one time. Once a person is sampled, you cannot sample it again. If it's done with replacement, then you may select a given number of the population more than once. Most real-world sampling is performed without replacement. The binomial model applies only to sampling with replacement. The hypergeometric distribution. If n is small relative to n, wait. Oh, come on. No, I forgot which is which. Isn't the capital N the full population, and then lowercase n is the sample? Yeah. Why? How does that make sense? They say if the sample size is small, then the binomial distribution is very good approximation. If n is no greater than 10% of n, then the binomial model can be used. Most national polls sample only about 1,000 people. They say most of the time you can just use this approximation. Wow! Can we ever just be done? Do we really need to know that fact? Whoa. Okay, now they were going to do some example problems. So anyways, let's skip all the example problems and hope that it's not going to be on the quiz. So, and then there's problems. Please tell me. Great, we still have 2 more sections to get through. Thankfully, they're very short because it only goes to page 231. Actually, no. Yeah, it does. That's it. We have this section, and the final section of the chapter is just the conclusion. So basically, we only have one more section. Which is the Poisson and exponential distribution. Yeah, here. Ooh, stop. It's a discrete distribution. It usually applies to the number that's occurring within a specified period of time. Number of events occurring. It's all of the non-negative integers are the possible values. Lambda is the parameter of a Poisson distribution is lambda. Able to produce different distributions. Say basic shape. That's the basic shape of a Poisson distribution. Is that literally it? The only thing that... Wait. What the heck is this? What? I don't care about the examples. And the times e to the negative lambda x. Oh, that's awesome. How much of this stuff do I have to memorize? Graph of exponential density function. And that's pretty much it. The conclusion is stupid. That was fun. I mean, it's mostly just key terms. I mean, a lot of it is just key terms, so maybe I should just look at this. Random variable. Wait, that's for the whole chapter. Please tell me the section it's in. Oh man. Never mind. We'll open up PowerPoint. So, here's the PowerPoint, which, well, it might be easier to find answers to quiz questions in there. And I'm treating it as an open book quiz because it's never stated anywhere in the course whether or not it's open book. It doesn't say it here. It says, okay, please don't fail. I have not failed up to this point. I don't think I really studied that much for the last quiz I took. And I still didn't fail. Normal distribution. It's a continuous distribution with two parameters, I believe. Stop. Oh, I have to go all the way down to 5-4. Where is it? 5-4. I'm just making sure. I don't want to get it wrong. It says it's in continuous, and there's two parameters. See? Stop. So, should be right. Sampling done without replacement means that you can only sample each member of the population once. So if the value of the standard normal z is positive, then the original score. Oh, great. I'm stupid. Where's z score? Where's z score? The number of standard deviations to the right or left of the mean. So, look at that. If it is positive, then the original value is to the right of the mean. Well, no, duh, that's so obvious. Why did I even have to look that up? Well, it's because I didn't remember what stop. I didn't really remember what z was. If it's positive, that means it's to the right of the mean. Whoa! My continuous probability distribution. A continuum of possible values. Which probability distribution applies to the number of events occurring within a specified period of time? I think that's Poisson. Let me just double check that. Oh, how do you spell it? Oh. Number of events occurring with the specified. Which of the following might not be appropriately modeled with a normal distribution? Oh, of course. Ooh, yes. Oh, really? Come on, now I actually do have to look at these examples. How am I supposed to find this? Where? Where do I find that? Like an example of normal distributions, and then please tell me examples of things that have normal distributions. Where? Where am I supposed to find those? Where, man? They don't even have it.
Seriously. They have examples for the other things. Dude, they don't have a list of examples. How am I supposed to know this? Oh, gotta be kidding me. I mean, why would it be in the PowerPoint? Dude, they don't... Did I just miss it or something, or what? How much time do I have left? 25 minutes. I have 25 minutes to find it, but I don't think they actually gave an example, a list of examples of what is described by normal distributions. Okay, wait, where is it? It doesn't do that. It just gives a very broad thing, like... Are you serious? What? Where is this even from? I have to go back to 6, because it's a dumb question. One reason for standardizing random variables is to measure variables with Actually, the answer to that is pretty close to this. To measure variables with different means and/or standard deviations on a single scale. The outcomes of successful trials are independent. Did they say independent? Binomial experiment. Oh, wait. Dang it! No, the outcomes are not identical. Tossing a coin is binomial distribution. Standard normal distribution has a mean of 0 and standard deviation of 1. And now we have to answer this dumb question. Dang it! Daily low temperature. Oh, come. Dude. Dude. Seriously. Why? Examples of normal dish. God, I'm kidding me. How am I supposed to know that? No. Not fair. It's not fair to people who are stupid like me. Returns. Come on. The daily
low temperature. I don't them even mentioning that specifically. I remember they talked about that actually. What the heck? Dude. Okay. What? Paper knife. I hate everything. I hate everything. I just single-handedly lowered my grade by a certain amount just now. I just lowered my grade. I lowered my grade